Today I talk about inefficacy of Gaussian regenerative amplifiers for quantum optical communication. And this work is collaborated with Oleg Gisbich, Saikat Guha, and Nobel Trutkenhaus. So as everyone knows, the photon loss limits the long distance quantum key distribution. So if we transmit single photon from either side to both sides through a logic channel, then with the transmission probability eta, the photon arrive at both sides, but with the rest of the probability 1 minus eta, photon is lost, and we couldn't get any signal. And in various quantum key distribution protocols, we have been observed that secure key rate is linearly scaled with the transmission eta. And we also know that the general upper bound on the secure key rate, and this general bound scales linearly with eta. So the key rate exponential decay with the distance for the case of optical fiber communication. On the other hand, we know that this exponential decay can be suppressed by, in the case of entanglement generation, by using quantum repeater schemes. The quantum repeater scheme is basically we use many middle stations through the logic channels, and we first distribute short distance entanglement, many short distance entanglement between neighbor stations, then gradually we purified and connected entanglement to get long distance entanglement. But this traditional quantum repeater scheme is based on two-way communication, so there comes another physical limitation, which depends on the distance and speed of light. But we can also find there's a new approach for quantum repeater that only use one-way communication. So in this case, the classical information is just needed to share inside the stations, and we can get better repetition rate of entanglement generation. Now, the interesting structure here is that this one-way scheme can be seen as the chain of lossy channel and black boxes. When we look at the classical communication, we can also observe that phase insensitive amplifiers interspersed between periodically interspersed between logic channels enable us to expand transmission distance. So both the case of classical and quantum communication, this structure of black box and logic channel chain enable us to achieve long distance transmission. So the question here is, what could those black boxes could be? So in this talk, we consider how a center stations modify the total channel. So how a center station modify the logic segment. And as a first step, we consider Gaussian operations. Gaussian operations are mathematically well defined, and experimentally implication is rather well established. And in connection with the classical communication, a natural question is, could phase insensitive amplifiers or general Gaussian quantum channels work as quantum repeaters? We'll give a negative answer to this question. Now, what is the Gaussian channels? So in order to show what is Gaussian channel, we will introduce Gaussian states. So we basically consider transmission of quantum states of light, which is a harmonic oscillator and described by two elements. One is displacement vector, and the other is covariance matrix. And displacement vector is average position of phase space, and the covariance matrix is the noise property of phase space. So it is a second order correlation of canonical variables. And in general multi-mode systems, the displacement vector is only is a real vector whose size is the size of the mode, and the covariant matrix is a real matrix that satisfies this condition due to the canonical uncertainty relation. Now, the Gaussian channel is the map that transforms Gaussian state to another Gaussian state. And this is described by two matrix, K matrix and alpha matrix. So given a covariant matrix, a Gaussian channel transforms another covariant matrix and displacement pair. And this K matrix is simply transform the displacement vector linearly. And the covariant matrix is transformed with this linear term plus alpha matrix. And this K and alpha will satisfy this condition due to the canonical uncertainty relation. So as a summary, so Gaussian channel is described by two matrices with single physical condition. And the Logi channel we usually talk about is a type of Gaussian channel. So which is described by this K matrix and alpha matrix, both is proportional to identity matrix. It's simply reduce the length of displacement vector and make a mixture of covariant matrix with the input and vacuum state with this transmission factor. Now let's go back to our problem setting. So we consider the Gaussian channel is sandwiched between two Logi channels, and we generally consider n-mode Gaussian channels. Now our central theorem is that we can decompose this Logi channel, Gaussian channel, Logi channel into this form. So a pair of Gaussian channels, one is at iris side and another is both sides. And we can correct Logi segment as a middle. In addition, we can say that this Gaussian channel at both sides is a unitary operation. So from this decomposition, we can basically know that we cannot reduce the effect of loss. And when we consider many stations interspersed between the Logi channels, but whenever these stations are Gaussian channels, then we can recursively use our decomposition so that we can push these middle stations at the iris side and both side and correct all Logi segments. And our decomposition is a property of channels, so it is not matter whether the input state is Gaussian or non-Gaussian. So this decomposition works Gaussian or non-Gaussian input state as well. Now let us tell our main implication, our theorem. So as I said, so the center station can be replaced with another Gaussian channel at iris side and another Gaussian channel at both sides. So we can consider this part as the modification of iris to state preparation, and we can regard this part as a modification of Bob's measurement. So we can, so any quantum communication protocol with the center station is equivalent to another protocol with the original Logi segment. So any QCrypt we can achieve with this Gaussian channel at the center station can be always achieved by another protocols without center stations. So this is our main result. And when we consider optimization over the input and output, then we can apply the general upper bound of secure key rate given by Takeoka, Guha, and Wild. And this also obeys the linear scaling. So this is our main result. And there's two remarks. So as I said, if we put the Gaussian channel here, then our theorem said that this is equivalent to another protocol with modification of input. So we are not sure the performance may or may not improve if we put the center station with keeping the transmitter and receiver the same. And the other remark is that our decomposition is mathematically telling mathematical equivalence. So our decomposition does not tell anything about technical or economical equivalence. So in this point, it is useful to recall the classical communication. So where the phase-insensitive amplifier is used periodically through the Logi channels, and as the phase-insensitive amplifier is a Gaussian channel, so we can use our decomposition, so putting our amplifier to this part mathematically. But there's another physical reason. Actually, we are using this setup in the classical communication. So up to now, we have introduced this specific decomposition. So this is an answer to the question how a center station modifies the total channel, so particularly Logi segment. But in practical, we would like to know as a single module how the whole channel looks like when we insert center stations. So in order to further address this question, in the following part, we consider general single-mode Gaussian channels and investigate entanglement breaking condition. An entanglement breaking channel is a measurement and prepare scheme, measurement and prepare scheme, and breaks any quantum correlation. So we cannot make entanglement of a secure key by using entanglement breaking channel. So it is fundamental to know that this 4 channel is not entanglement breaking, because if it is entanglement breaking, then there's no way to use for quantum communication. And as a simple observation, if we put the center station entanglement breaking, then whole channel becomes entanglement breaking. So all we have to concern about is non-entanglement breaking center stations. And note that pure Logi channels are not entanglement breaking for any positive transmission. So now we concentrate single mode Gaussian channel and non-entanglement breaking stations. For the single mode Gaussian channels, we already know much about the entanglement breaking property. So in this paper, we can find a unitary equivalent classification of single mode channel, which is in any single mode Gaussian channel can be decomposed with the sequence of unitary, standard form, and unitary. And standard form is basically the diagonalized K and alpha matrix. And according to this paper, there's only 2 of non-entanglement breaking center stations. One is phase-insensitive channel, which is phase-insensitive amplifier or attenuator. And it possibly comes with a phase-insensitive uniform noise. And the other type of channel that could be non-entanglement breaking center station is additive noise channel, so which has the noise at one direction of phase space and does not change the displacement vector. In both cases, we can write down general form of the non-entanglement breaking center station sandwiched within Logi channel, and we can simply determine the condition that 4 channel becomes entanglement breaking. So this is the formulation. And in the following part, we'll apply this general result for a specific example of quantum limited amplification. And one of the important amplifier is phase-insensitive amplifier, which is squeezer and is a unitary operation. And as this is a squeeze unitary, if you pick up this part or this part, then both of them are not entanglement breaking because this is unitary equivalent to pure logic channels. So the question is, such a unitary channel can make the whole channel entanglement breaking. So according to our result, this center station does make the whole channel entanglement breaking when the squeezing gain is large enough. So we must be careful to use the center station squeezer in order not to fulfill this condition if we want to use this for quantum communication. And this is an example that a unitary center station makes whole channel entanglement breaking. And another important class of amplifier is quantum limited phase insensitive amplifier. So which is the ordinary amplifier. And according to our result, this even the quantum limited phase insensitive amplifier make the whole channel entanglement breaking if the amplification gain is large enough. And as a simple observation, if we consider long distance logic segments, so that means each of transmission of logic channel is much smaller than 1, then we can simply see that both of this condition, both of right-hand side of this condition approach to 1. So this means that the gain is nearly equal or larger than 1, but this is always satisfied. So this means that for long distance transmission, a small gain amplifier renders whole channel entanglement breaking. So I recommend not to use the amplifier for repeater stations. Now let me summarize our talk. So we have observed linear scaling of QCrypt, and in order to break the QCrypt, there exists this structure of black boxes. But if we consider the center station of Gaussian channels, then there's no way to break this linear scaling. And we also determined the condition that the center station, which is a single mode Gaussian channel, makes the whole channel entanglement breaking. And using this general formula, we observe that we give a special example for quantum limited amplifiers and observe that small amplification could make the whole channel entanglement breaking, and we are better off using amplifiers as a repeater stations. Thanks for your attention.
I was wondering, have you considered a non-deterministic Gaussian operation? Because I would believe that a non-deterministic Gaussian operation could be useful for quantum communication, such a noiseless linear amplifier, for example.
Yeah, so we have no idea when we consider the non-deterministic case. So maybe probabilistic probabilistic Gaussian operation may work. And yeah, we don't have a definite answer for that question.